Okay, we're going to start by talking about 6.1. This is where, oh, where are my electrons? The learning goals for this PowerPoint, we're going to look. Students should understand the Octet Rule as a general rule for electrons. We're going to talk about this. This basically means just we're going to talk about how electrons are constantly seeking, or elements and atoms are constantly seeking stability. And one way that they can be stable is if they have an octet. Which means 8 electrons. Number 2 is electrons exist in orbitals and sublevels, and so we're going to talk about where the electrons are located within the around the atom. What students will be familiar with the Aufbau principle, the Pauli excursion principle, and Hund's rule. These are definite definitions that you need to know, so definitely know the definitions of those and also be able to apply those. So that's number 3. Number 4 is students will relate electron configuration to the periodic table. So we're going to look and see how the periodic table helps us understand electron configuration, how to write electron configuration from the periodic table. So let's dive into this. What we know so far. We've studied the Bohr model of the atom. And we're looking at the Bohr model, and we can also call this the Bohr model, or you can call it the planetary model, because basically electrons orbit the nucleus, so they go around, and we see little red dots, and they're moving around the nucleus. Okay. Now, the electrons must travel at a specific distance from the nucleus. So in the Bohr model, basically they stay the certain distance and they constantly move around the nucleus. That's why we call it the planetary model, because it's kind of like orbiting how planets orbit around the sun. Now, these distances are called orbitals. So how far away from the nucleus we are, those are orbitals. So here's our first orbital, here's our second orbital. And we talked about how when we absorb energy, it causes electrons to move higher. So we talked about the bright line spectrum and how when you absorb energy, that electron can move up an orbital, and then as it drops back down, we see that it emits light. And we see those as bright line spectrums. And we've seen that so far. And so this is what we know. We know the Bohr model of the atom. But what happened is we see something happen when you take a single spectrum line. So we take one spectrum line from our bright line spectrum and we put it through a magnetic field. So we have a north and a south, a positive and a negative. And basically what happens is that one emission line would break up into 3 separate lines. And what we see is that basically what happens is there has to be something else there. It broke up into 3 different lines. And so basically what this means is that not all atoms in the orbital are equal electrons. So basically what we're saying is there must be suborbitals. So as this one line breaks up into 3 different lines, we call these suborbitals. And these are where electrons are going to be located. Now, the orbitals that we're going to be talking about are S, P, D, and F. The first one is the s orbital. It can contain a maximum of 2 electrons. Now, every sublevel, so we look up here, every suborbital can contain 2 electrons. Now, in the s orbital, there's only one sublevel. Okay, so in the s orbital total, it can only carry 2 electrons. It has a spherical shape, meaning it's a sphere. It looks like a ball. You can think of a baseball or basketball, whatever. That's a sphere, and it has that shape. There's a 90% probability of finding an electron, so actually finding the electron there. And the first 2 columns on the periodic table are the s orbital. We call them the s block, and we're going to talk about that and look at the periodic table and point those out. Okay, the next orbital that we have is the p orbital. It starts in the second energy level and has a maximum of 6 electrons. So if 6 electrons can fit into the p orbital, we know that 2 electrons fit in each sublevel. Well, we look and we see that p is going to have 3 different sublevels. We have px, py, and pz, and you can kind of see them over here. The main thing is that we say that the p orbital can be broken up into 3 different sublevels, or 3 different orbitals that we see. And so the shape that this has is going to have a kind of dumbbell shape. And we can kind of see them all over here. Now the entire p orbital would be made up if all of these guys were put together. That's the entire p orbital. And in the p orbital, we see that broken up into those suborbitals, and that's where we'd have 2 electrons here, 2 electrons here, and 2 electrons here, for a total of 6. Okay, they are group 13 through 18 on the periodic table. We call that the p block, and we're going to show you more of that in just a second. Now, dealing with the s and p orbitals, that is where we get the octet rule. Okay, now the octet rule is incredibly important to chemistry. It's incredibly important to bonding. All atoms are trying to become stable. Okay, we looked at nuclear decay earlier, and we talked about that. And in nuclear decay, we see that they're trying to become stable. Well, in chemical reactions, they're doing the same thing. They're trying to become stable, trying to become more stable. And most atoms that we study in the class have an atomic number less than 36. And these atoms are most stable when they have 8 valence electrons. Okay, now they have 8 electrons in their outermost energy level. That's the definition of a valence electron. It's the electron in the outermost energy level. Okay, and everything is trying to get to 8. 8 is great. 8 is where you want to be. It's really important. So the octet rule, it happens when they have an octet, their p orbital and their s orbital are full. So you have 2 electrons in the s, you have 6 electrons in the p. That gives you a total of 8. When your s and p block, when those guys are full, those orbitals are full, you have an octet, and that's what everything's trying to get. Now, the other orbitals that we have the d orbital, which it starts in the 3rd energy level. Okay, the only thing in the first 2 energy levels are going to be s and p. In the 3rd energy level, we bring in d. Now it has a maximum of 10 electrons can fit in the d orbital. So if it has 10 electrons, we see that it has 1, 2, 3, 4, 5 sublevels. And those are the 5 sublevels that we're going to have. We designate these as -2, -1, 0, 1, and 2. Okay, there's a 90% probability of finding an electron, because these orbitals that's where we have the highest chance of finding those electrons. And basically the d orbital is in the transition metals on the periodic table. These are going to be called our d block. The last orbital that we have the f orbital, and we see that it can hold a total of 14 electrons. And so if it holds 14, we see that we have 1, 2, 3, 4, 5, 6, 7 suborbitals. And basically this takes up the lanthanide and actinide series on the periodic table. So we look at the periodic table. Okay, ever wonder why the periodic table has a crazy shape to it? Okay, the reason why it's structured like this is because of electron configuration. Now, the blocks, we talked about this. Now, when we're looking at what we call s block, or we're looking at the s orbital, that takes up our alkaline and alkaline earth metals right here, and helium. Okay, and helium is kind of be a part of that. The reason why helium is in group 18 is because it is stable with 2 valence electrons. It's the exception to the octet rule. It's happy with 2. We call that the duet rule. And it's just we put it over there because it's completely 100% stable and it stays there. But it is part of what we call, this is the s block. Okay, now the next orbital that we have our p block. That's group 13 through 18. That's going to be our p block. Okay, and it sits right there. Okay, the d block, or the d orbital, is going to be in the middle right here. That's d. And then we see our lanthanide actinide series, these guys down here. that is going to be our F. Okay, that's our F block, which is down on the bottom. Now, when we're looking at these, when we're looking at our energy levels, we're going to see that our energy levels are going to be designated by the period on the periodic table. So 1, 2, 3, 4, 5, 6, 7. And we'll talk more about this when we're talking about the off-ball principle. But this is why we get our shape on the periodic table and how it's set up. The one thing you can think of and look at it, remember S block, remember S orbital, how many electrons can it contain? It will contain 2. Well, we have 1, 2. Okay, if you look at the P block, how many electrons can go in the P block? Well, 6. And we see we have 1, 2, 3, 4, 5, 6. D, it can hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then lastly, we see our F block, it should be able to hold 14. We count these out, and what we'll see is we get 14. So the periodic table is set up according to the orbitals for our electrons and how they fill. So let's look at some examples. Example A1, the emission lines of a sample are put into a strong magnetic field and split into 7 distinct lines. What is most likely the orbital of the electron is transitioning from? So what we're looking at is we see that we have one line, and this is a Zeeman effect. We see one line broken up into 7 lines. Well, what has 7 suborbitals? We know that that would be the F orbital, because it can hold a total of 14, which means it has 7 sublevels. Okay, so we see that this one line is broken up into 7 lines, so therefore it's going to be the F orbital. Looking at our next example, we see we have A2, and it says these 3 lines show the probability of finding electrons versus the distance, and we see identify each orbital in the picture. So we see the distance is really close, so this is going to be our 1s, why it's really close and there's a really high probability of finding an electron. We can see this green one right here, and we see this is what we have. It's really close as well. There's a decent chance. We see there's a little bump right here, so that green line is going to be our 2s. And then we see right here, the red line will give us our 2p. Just because of the distance from it, as we know it's very close to the nucleus, and there's a high probability for each of those.